So this is lab number 2, motion of a falling object for physics 2211. The purpose of this experiment is to compare the motion of an observed object falling to two computer models, one including only gravity and one including both gravity and drag. In this lab, I recorded a video of a paper ball dropping from a height and compared it to both models. So the fundamental physical principles, close to the Earth, the force of gravity is just mg, where g is the acceleration due to gravity, with approximately 9.81 near the surface of Earth. And the general gravitational formula, which is F, equals gravitational constant times the mass of one object times the mass of the other object divided by the radius squared between the two objects. And so close to the surface of the Earth, just because the Earth is so massive, this ends up simplifying to mg. But like if you wanted to know other gravitational forces like in space, you could use that one. And then the other fundamental physical principle is drag, which is b, which is a constant, and v. This just means that drag is proportional to velocity squared. B is really complicated and doesn't really matter here. All that matters is that drag is proportional to the square velocity. Experiment initial conditions. The mass of the paper ball is about 4.5 grams. The initial position is 0, 1.30, so 1.3 meters up in the y direction. The initial velocity is 0, 0, 0, so it was completely at rest. The system is the paper ball. The surroundings are the air, the floor, my hand, so everything that's not the paper ball. And here is a quick video of the experiment.
Okay, good. Okay.
This is my model without drag, so it just assumes there's only gravity. So I put in the system mass, I put in the initial conditions, I set b equal to 0, and then set it. Calculating the net force is just me updating Fnet, but in this case, since b is 0, it doesn't actually, the calculating F drag doesn't do anything because you're just going to multiply it by b, which is 0. I just did it to make my code easier. And then Fg is negative g times the mass of the ball in the y direction only. And then we apply the momentum principle to get the new velocity and apply the position update formula to get the new position. And then with drag, this assumes both gravity and drag act in the ball. So the only code change is just I set b to a very small finite value instead of 0. And that just applies the drag force because previously it was 0, so there's nothing, and now it's 0.002, which I found to be correct with my experimental results. So this is figure 1. The experiment is the blue line, the model without drag is the orange line, and the model with drag is the green line. So you can see how the model with drag more closely conforms to the experimental results. Some sources of error, there was some upward or downward velocity from my hand, maybe. When I dropped it, like it wasn't completely at rest. I could have tracked it poorly, leading to inaccurate position data. There could have been some wind in the lab causing the ball to float side to side, or the ball could have been packed too tightly, leading to like not enough drag force to be noticeable at all. What if imagine the object was initially thrown downward with the terminal velocity, in this case, be the same or different from the case where the same object was initially dropped from rest. Justify your answers by using your computer models. So in the model that only uses gravity, there won't be a terminal velocity, but when there is a terminal velocity, it will always be the same. You see how the velocity versus t is going to converge on an asymptote. My trial, like I didn't drop it from a high enough height, but it would converge on something, yeah. So it would be the same terminal velocity however fast you dropped it. What does it mean? Examine the velocity versus time. Which models, if any, predict terminal velocity? So the model with drag, which is on the right, predicts terminal velocity because the velocity is curving towards an asymptote, whereas the model on the left will not have a terminal velocity because the velocity will just keep increasing and increasing in magnitude. Terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. That means the net force is equal to 0 and it will travel at constant velocity. Conclusion, I compared my experiment to my computational models. one model with only gravity, the other model with gravity and drag. My models were in GlowScript with initial assumptions from the experiment. In the experiment, I dropped a paper ball from about 1.3 meters. I then recorded its motion using tracker and compared it to my models. Both models were slightly inaccurate, but the model that factored in drag was a little bit better. And these may be due to giving the ball initial velocity, tracker errors when in the lab, or among other errors.